This is a talk called Understanding Heavy Truck Event Data.
With part two
With part two, he's going to talk about something about electronics. I'm a software guy. I never understand anything he says. So what does this talk about? It's about data stored on heavy truck engine control modules, communicating with them, and reverse engineering proprietary diagnostic protocols used by heavy truck ECMs in the context of accident reconstruction. So the outline, background information, what are ECMs and what is HVEDR data? That's mostly what I deal with on a day-to-day basis. And then I'm going to work through an example of reverse engineering ECM network data. So heavy truck crashes, semi-trucks, big over-the-road trucks, haul lots of stuff. They crash into stuff all the time. In 2008, there were 380,000 of these things involved in trucks just that year, or involved in crashes just that year, 4,000 of which were fatal, and 66,000 were injury crashes, including the fatalities. Average cost per crash, according to, I think, NHTSA, is over $148,000. If it's an injury crash, that goes up to $331,000. And if there's a fatality, that goes up to $7 million. In the U.S.? Yes, in the U.S. Expensive crashes lead to lawsuits, and lawsuits lead to forensic examination, which gives rise to the field, the profession of accident reconstruction. So the accident reconstructionist's job is to review the data and determine who is at fault. If they're law enforcement, that could lead to criminal charges of negligence, and if they're private and they're working for an insurance company, that can lead to civil claims. So the parties involved are insurance companies, law enforcement, and attorneys. Those are the three people who you always try to avoid in your day-to-day life: insurance companies, cops, and lawyers. Those are who I have to deal with all the time, so feel bad for me. Scientific reconstruction traditionally uses physical evidence such as deformation of the vehicle and measuring skid marks on the road. You can do some math with weight of the vehicle and then coefficients of friction, and then figure out who is going how fast and who hit who when. And then in recent years, you end up with these things called event data recorders. So this, those of you who are sitting close enough can see this. It's a passenger vehicle event data recorder. It's its own dedicated box. Usually they'll be somewhere under the dash. People call them black boxes. Almost none are black. This is one of my pet peeves. They're all silver. So if you want to call them silver boxes, that's fine, but not black boxes. They're typically integrated into an airbag control module, and they, depending on the model, they weren't standardized until just a couple years ago, so it was kind of a crapshoot what you'd get before then. And they would record speed before the crash, brake usage, whether or not the driver was buckled up, stuff like that. And it's a purpose-built device, which is great for forensics. All this thing does is it wakes up, it decides, hey, do I need to deploy the airbags? If it does, then it records what's called a deployment event. If it doesn't, it records what's called a non-deployment event. And then it's read by a special tool called the Bosch CDR kit in most cases. And that's it. For forensics, that's great. Heavy vehicle EDRs are a completely different beast. They're not legislated. Heavy trucks are not required to have them. I think what happened was the government regulators went to the heavy trucking industry and said, hey, you should really, really include this stuff in your engine control modules. Otherwise, we may be forced to legislate you. This is not a veiled threat. It was a veiled threat. So they all began implementing this stuff. Began showing up in the early 90s as an add-on, but nowadays it's standard in pretty much all of them. And it's extracted using maintenance software, not actual forensic software like the Bosch CDR kit. It's the same stuff that you would use for driver information reporting or maintenance and diagnostics. So the data, like I said, it's in the engine control module, whose primary focus is controlling injector timing, all the stuff that an engine computer does to keep the engine running right. Because if you caught our talk on Friday, I think we talked about how data hungry the trucking industry is. They said, oh, we have these computers and they can store data, and we can gather all this data that'll help our fleet customers be more efficient in their business. So maintenance history, they track driver behavior. Some ECMs actually have a mechanism where if a driver is really good on fuel economy, it'll raise the vehicle speed limit for a little bit. That's called the driver reward. So if you're really good, it'll let you cheat on the speed governor a little bit, which is an interesting motivational tool. It also stores fault codes, so mechanical faults. You know, if your car is throwing a check engine light, you go down to O'Reilly's and they have that cheap little scanner. Same kind of thing, but more full-featured. And what we're interested in, crash event data. And all of this may be interesting in a forensic context. So maintenance data, if you can support a narrative where the fleet was negligent on maintenance, you can go to the fleet and sue them or pursue criminal charges. So issues with heavy vehicle ECM forensics. The maintenance software is not great as a forensic tool usually. Many of them delete evidence. Some of them, if you forget to uncheck a box, it clears all this data. On other ones, if you click next and then it comes up, do you want to delete this data, yes or no? And yes is right under where your mouse was to click next before, so if you're not paying attention. Stupid stuff like that. It's also stored insecurely. That's a different talk, but the cryptography that they use for their secure file format is stuff like a password-protected zip file, and it's all one password, and I have it written down someplace. And vehicle impacts frequently cause data loss. Imagine that. So if you're storing your data in such a way that the thing that you're trying to record causes your software to not read it properly, that is a problem. Speaking of data loss, so I'm going to just kind of run through a case study. It's kind of boring if you just talk about this stuff in general, so I'm going to go over a specific case where we solved this problem. Let's play this video. I hate computers. Go. Did it seriously just copy over the screenshot? Okay, I have some still images of the aftermath in a few slides, so we're just going to go off of those. Imagine that city bus over there just had a school bus crash into it and the carnage was glorious. I just need you to imagine that for me. So he crashed a bus on purpose. I occasionally moonlight as a crash test engineer, and it was an experiment to verify that the HVEDR data stored on board actually matched what happened in the real world. The plan was crash bus, connect software, download data, so then we have the data, and then we have all the stuff from our accelerometers and GPS and everything, and then we would compare it in Excel and do science. So here are some gratuitous carnage pictures. That's pretty good. That's a pretty good delta V right there. That's from the inside of the bus when I was trying to recover some of the equipment. So as you can see, if you were seated on that side of the bus, you would have been road pizza. It would have been pretty bad. So we were going through and trying to extract the data, and this is a picture of us going through. And you can see the sudden decel event, or I'm sorry, this cat calls them quick stop events. So we have the, so good, it recorded a quick stop event, awesome. So we go to extract it, and it's going through and receiving data. I'm thinking that I'm going to get to go to bed early tonight, which is kind of a rare occurrence on these crash tests. Oh no, it was unable to retrieve snapshot data. So after buying a case of Mountain Dew, I had to get into it. So surprise, surprise, when buses hit stuff, they break stuff. And power loss during event writing causes data loss. So the way these ECMs work is all of the event data recorder data is stored as a series of frames. And when it detects this speed loss, it's not like a passenger airbag where it has an accelerometer and detects a shock. It just detects a sudden drop in wheel speed, which is transmitted over either the J1708 or J1939 bus. And if it's interrupted while it's writing, then you get an incomplete record. But can we get it back? So I'm really sorry. I was assuming I was going to have a projector today, but I don't. This is the logged network traffic, if you can all squint. So this is over J1708, and it's kind of a degenerate transport protocol that this manufacturer invented. Because I looked at it and I saw increasing sequence numbers and everything, and I thought, man, that's weird, but that's not how J1587 does transport. Well, this is a thing that they invented, and you can see that there's 3 messages within each record, and then this byte over here increments by 1 every time. But then, and there's this kind of request response framework where it says, hey, I want this frame, and then it gives it to it, and then it says, I want this frame, send it. And then here it just says send it, send it, send it, send it, send it, which is the software going, are you there, guys? Hello? After which point, when it gets no response, it just throws everything away. So power loss caused only the last few frames to not be extracted. And the OEM software just took its toys and went home. It said, if I can't get the whole thing, I'm not giving you anything. So if we decode the traffic, we had cheat codes because we had GPS and we had a few different IMUs hooked up to this thing. So doing manual analysis of the speed data, we found something that looked a lot like what our GPS logs showed the vehicle speed was. And it was the J1587 format, 1 byte miles per hour times 2. And the records in frame appear to follow a PID value format. In this case, the PID was 32. So this is road speed as we decoded it. And then, so how close were we? As you can see, we've plotted on the same axes the actual road speed. We logged it as it was transmitted across the bus live. And then along with the recovered EDR speed, and then we also recorded using GPS road speed and actually using a few different methods. We logged speed, and as you can see, it's basically dead on for all of them, and it tops off at 27.5 miles an hour. So the takeaway from that is that kind of destruction can easily happen at low speeds. Don't text and drive, please. And the takeaway from all this is we now have a well-verified forensic methodology for recovering partial ECM data from power loss. Decoding the other PIDs required dumping a proprietary database made by a fly-by-night operation in Florida several years ago over COM using Python, which is something I don't want to get into because it caused me to lose a little hair. But at the end of that, we were able to decode all of these records, including the ones that we didn't have cheat codes for. So now we can extract this stuff without the buggy software that we were trying to work around in the first place. And with that, I will hand it over to my electrical engineering friend.
So I'm going to talk about some of the background that led to what we were able to do with the stuff Haystack there talked about. So one of the problems we have with doing research with heavy trucks is that they're extremely expensive. Earlier we showed you that crash. We were very lucky to have access to a school bus and a city bus that had been decommissioned, and that was a conference for a bunch of accident reconstructionists. So somebody was willing to destroy those, but that's pretty rare. So for our day-to-day research, we had to build a tool. It isn't very common for like a big trucking fleet or someone who owns a truck to just let you have access to their vehicle and potentially do things to it that could destroy it or disable it or cause them monetary harm. So we had to build a device. So the device we ended up building was called a truck in a box. And again, sorry for the small picture since there's no projector. But the device here, we essentially, oh, sorry, I'll go back a little bit. We took all of the electronics from the inside of the engine compartment this is a Navistar ProStar with a Max Force 13 engine, and put the electronics in this apparatus and hooked up a bunch of sensors to convince the electronics that it was in an actual vehicle, and powered it up and turned it on and started doing stuff to it. This was an incredibly tedious process. You can see this was part of the wiring harness going to the ECM. This was handmade. I think there were something like 200 or 300 wires in this apparatus. So the Truck in a Box project was originally funded by the DARPA Cyber Fast Track program. So thank you to Mudge, if you know who Mudge is. We assembled all those components into a box, and then we actually had a semi-functional vehicle that we could test on the bench, and we could do things to it that you wouldn't want to do to a real vehicle that could potentially destroy it at almost no cost. So to recreate all of the things inside the vehicle, we had to create the J1939 Network, which is a basic CAN bus, which is not complicated. Lots of people have talked about that. The older legacy J1708 bus, and we had to kind of roll our own electronics for that, and we talked about that in our talk on Friday. And there's some stuff on GitHub if you are interested. We had to hook up and simulate passive sensors, which were just resistors and potentiometers and things like that, so that we could set the oil pressure to a value where the ECM didn't think it was having issues. And then we had to simulate some more active signals. I'll talk about that more in a minute. Some of the manufacturers publish voltage values for some of these sensors. So we were able to simulate those pretty simply by just reading the manual and hooking up the resistor values. But some of them we actually had to reverse engineer. So in the first Truck in a Box, we had the main engine control module, the instrument cluster, and then rather than actually install these two other modules, the body controller and the brake controller, we ended up recording traffic from a real truck and just playing that traffic back at the other two ECUs so that they thought it was in the box. It turns out that their functionality is simple enough when the key on the ignition is off that you don't really need to do anything other than broadcast a few CAN messages. We used a thing called the National Instrument C Rio to broadcast all of those simulated traffic messages. We also used that to simulate some of the more complicated analog sensors that I'll talk about in a second. And again, the passive sensors were done with potentiometers and resistors. So these active sensors, there's a bunch of sensors on the ECMs that don't work like a resistor. You have to, they change over time. So they're like a pulse width modulation or like a sine wave, and the ECM does pulse counting to figure out what's going on. So we've got two sensors that the ECM was particularly frustrated that it could not see when we hooked up to it, and it kind of refused to do anything until we solved those problems. One of them was the accelerator pedal. With no accelerator pedal, it wouldn't do anything. Even though like a resting truck is just sitting there, the accelerator pedal is sending a position as long as the power of the truck is on. So that was a PWM signal. We hooked up a microcontroller and solved that one in a couple hours. The more complicated one was the vehicle speed sensor. This is the sensor that actually is on the mechanics of the truck that helps it determine how fast it's going down the road. So again, apologies for the small picture because of the no projector, but this is the, this laser pointer's not going to work. In the middle here is a toothed ring. That's the vehicle speed sensor's tone ring. And then off to the left is a little black nub looking thing. That's actually a magnetic pickup, and it can detect the changing ridges in the ring. So we bought the tone ring, we hooked it up, and it was kind of complicated because you have to spin this thing pretty fast to get it working. So we rigged up an adapter that we cut out using some prototyping equipment, and hooked up a remote control. And since this is something spinning very fast using some welds not by somebody who knows how to weld. We hid behind something metal after we spun it up, and eventually we figured out that it was safe and it wasn't going to fly apart, we hope. So there's a picture of it spinning in a vise hooked up to holding the sensor near it. And we ended up getting this signal on an oscilloscope, and it's just an AC signal at about a kilohertz, and the frequency varies depending on how fast the vehicle is moving. The unfortunate part for this is that the signal can reach up to 100 volts peak to peak, so basic, like a microcontroller, can't do that. So we had to use the National Instruments CRIO to generate a rail-to-rail signal. So we spun it up, we got it up to 3,000 RPMs. I believe the final vehicle speed was something like 85. And we fed that into an ECM, and magic, the ECM converted the analog signal into a CAN message on the network. So it actually thought it was moving, and it passed that message along to the instrument cluster, and it actually started counting up miles. So it thought it was going down the road, even though the key wasn't off and there's actually no engine. It was kind of fantastic. Eventually, we ended up building a more safe apparatus with this enclosure around it in case the thing ever decided to fly apart, because metal things spinning at 3,000 RPM is like to fail. So we built this apparatus that was much more reliable, and we were able to use it for several years. And then here's a picture of an instrument cluster we rigged up, and we're feeding the ECM the signal, and then the ECM is broadcasting the CAN traffic, and then the instrument cluster is receiving it. So that's nice, but what's that good for? Well, that's not particularly useful for security analysis, but we can do some reverse engineering on the ECM to figure out how it stores some of the data. So as James was talking about earlier, these devices store event records for when you slam on the brakes or something bad happens. So that gets stored in flash memory. So we can use our fake vehicle speed sensor to put in a pattern that we know what it looks like, run the ECM through that simulated driving pattern, and then slam on the simulated brakes, and the vehicle will record that as a crash or hard brake event, and then we can go fishing around in the flash memory for that pattern to see how it stores that data. Now, that sounds simple, but it's terribly complicated. The first challenge is these ECMs are incredibly rugged. So in cars, ECMs are just like a little thin metal can, and maybe the circuit board inside has some simple coating over the top of it. But with the truck ECMs, these things are like cast aluminum. A lot of times they're epoxied into the case. And the whole point of that is they have to go for millions of miles and endure road grime, oil, all kinds of stuff that can get all over them. And so here's a picture of the inside of an ECM. This is the inside after we opened it up of one we found. And you can see the little patch, if you're close enough, where we had started to clean away so we could get to the flash memory chip. It was just disgusting. And we don't even know what this is. It could be oil, it could be road grime, it could be anything, but it was covered, even on the inside. And there's a gasket seal around this ECM. This was an older one that was pretty simple to open. All we had to do was take out some screws and pop off a rubber seal. But that was probably the only time we ever encountered that simplicity. Most of the ECMs we had to mill apart. So you can't see it here, but this is an ECM where we are milling the connector housing off the top of it so that it will release the circuit board so that we can get to the components that are hidden from us. So once we spent a few months disassembling all these ECMs, breaking several of them at a couple $1,000s a pop, we had to clean the boards up. We had to get road grime or whatever off of them if they were surplus. Then we had to get the conformal coating, which was part of the protection, not protection from me, protection from road grime and such. We had to get that off, and some of that requires different caustic chemicals depending on the material they used for conformal coating. It could be acrylic, it could be an epoxy. Some of them we couldn't figure out, and just the solution was to leave it sitting in a chemical bath for a couple of days, and eventually it flaked off. Sometimes, so did some of the components. So we eventually get a bare circuit board. We use a hot air rework station to get the chips off of the board, and then we used a universal chip reader to get the data off the chip. These are just a generic device you can buy from a company like Dataman or Zeltec. They have a socket for different ICs, and if you're lucky, they make one for the chip you've got, and and then they've got an algorithm for extracting it. So we didn't have to develop the algorithm for removing the data from the chip. So there's a picture of one of the flash chips that we got at. This one was clean beforehand, and this still has the conformal coating on it, but they're relatively simple devices once you get them off the board. So here, again, sorry for the small size, you can see some raw hex data, and then that's the engine serial number highlighted. So we've actually got access to some of the internal data. And then here we found the hard brake event. This is the record of actually spinning up the vehicle speed sensor and then stopping it suddenly, and it reporting, oh, hey, I went through a hard brake or crash event. So we were able to extract that data from the chip. So even if the ECM is in pieces, as long as that chip isn't cracked in half, we can get to it. So the conclusions, reverse engineering these ECMs is not impossible. It's a lot of work. But we can go from the analog input data all the way down to the internal hex storage stuff on the flash chips. We can simulate things that you could never do to a real vehicle, like crash it into a wall, because I mean that would be one, expensive, and no one wants to buy a truck just to crash it into a wall except NHTSA. So we were able to do that in the lab and then reverse engineer all of the stuff. For future work, we're looking at tearing open some of these newer ECMs. We were very lucky in that most of the older ones had a separate flash storage chip. Some of the newer ones, they integrate the flash storage into the same package or on the same die, and that makes it a lot harder. I can't just pull it out and stick it in a reader. We're looking at doing ECU analysis for some of the other units, like the brakes and the telematics units. So we'll hope to be presenting about that in the future. Thank you very much for your time. We've got plenty of time for questions if anyone has any. Again, sorry for the lack of projector. So if you want to come up and see any of the pictures, feel free. Yeah, we gave a talk at the main conference on truck hacking, and we'll put it up on the GitHub. I think that's truckhacking.github.io. Give us like a couple of days to get home from the conference and put those up, but we'll put them up there.
What's it again?
Truck hacking, excuse me. Yeah, github.io. You want to say anything?
Thanks, everybody.